Welcome to a new lesson of heat transfer. Today we keep studying internal flow convection and we carry out general thermal analysis for internal flows. You can see here a section of a pipe and we have a flow going from the left to the right, so in this way. And so what's the energy balance for this control volume here that's bounded by this dashed line? So we have a flow coming from the left and the internal energy of this flow is m dot Cp times Ti, the inlet temperature, and the energy leaving the fixed control volume is m dot Cp Te, the exit temperature. And in general these two internal energy are different because we inject in heat, for example, for a heating problem. So Q dot is equal to m dot Cp times the difference of the mean temperature. So the mean temperature, the exit Te, and the mean temperature at the inlet or the initial Ti. So for this type of flows, we can have two different boundary conditions in general, the two simple cases. So in the case of constant temperature, the temperature of the surface, Ts, is constant. So this would occur, for example, if you have boiling or condensation outside of the pipe. Whereas instead we have an electrical resistant heating on the surface of the pipe, we have a constant heat flux. So this Q dot W is equal to Hx, the convection coefficient, times Ts minus Tm, where Ts is the temperature of the surface, Tm is the mean temperature we defined in another lesson. So let's study first the case of constant surface heat flux. So in this case, Q dot W is constant, so BQ, the heat transfer rate, equal to Q dot W times the surface area, is equal to m dot Cp, the specific heat capacity, times dTe minus Ti. So we can rearrange this expression. So Te, the exit mean temperature, is equal to the inlet mean temperature times Q dot W times As divided m dot Cp. By As, the surface area, it's equal to the perimeter, that's assume it's constant in our case, times x, the streamwise coordinates. This means that everything else is constant except x. So x grows downstream, obviously. So we have a linear increase of the mean temperature with x. What happens instead to the surface temperature if you have Q dot W, so the heat flux of the wall constant? We write in this way, we rearrange, and again, we can see that we have Ts equal Tm plus Q dot W Hx, but Hx is constant, Q dot W is constant, so Ts grows just like Tm, so Tm grows linearly with x. Also the surface temperature of the pipe grows with x, so we can sketch this and see what happens in the case of constant Q dot. So in fully developed conditions, we have the same growth of Ts, the surface temperature, and Tm. So they both grow at the same rate. But of course, we are warming the fluid from the boundary, from the wall, so the surface temperature is larger than Te, the mean temperature. And of course, the linear growth is only true for the mean temperature also in the entrance region. And this is true only if you have the assumption of constant properties. So a bit of maths can also show that the partial T at any location R, radiant coordinate, is equal to the gradient of Ts over dx and dTm in dx. So and this one is equal to Q dot times the perimeter divided by m dot Cp. So this means that if you have a constant heat flux at the wall, the temperature profile has the same shape along x. So of course the the temperature grows because we are injecting heat into the pipe, but the shape as a function of the radial cone will be the same. So what happens instead if you have a constant surface temperature? So Ts is constant. In this case, the mean temperature Tm is not growing linearly with x. We can still define the heat transfer is equal to Hx times the surface area times a certain average temperature difference between Ts minus Tm. The problem is, how do we define now this temperature? Because in the constant heat flux, this difference here did not depend on x, but now we have an undefined growth. So one way to do this is to define an average temperature. This is just an approximation. We assume the growth to be linear, and we define a temperature difference between Ts, an algebraic difference between the temperature at the exit, mean temperature at the exit, and the mean temperature at the inlet. But this growth is only an approximation, because the growth we see here, it's not linear. As the flow develops downstream, Tm, the mean temperature here depicted in pink, only approaches Ts asymptotically. So there's not a linear growth as x grows. And we're also sketching here the third surface temperature Ts. In this case is constant. So to find an exact definition for the average temperature, we can do a differential energy balance between the change of internal energy and the heat that's injected. So we rearrange this. So we move the temperature to the left and everything else to the right, and we integrate the left-hand side from the inlet temperature to the exit temperature. And by integrating, we find a natural log here. We can rearrange and express the Te, the mean temperature at the exit, as a function of an exponential function, which depends linearly on x here, the exponent. We can take that expression and we can solve for m dot Cp this way. And so we substitute this expression into the definition of Q, and we find that Q dot is equal to Hx times the surface temperature times a new temperature difference that's a function of Te, Ti, and Ts. So what's this expression here? So if you redo the algebra, here you find this expression for the temperature difference. So at the bottom here, we have a log term of the ratio of these two temperature differences. This quantity is called the log mean temperature difference. So you can see it involves Ts, Ti, Te. This is an exact representation of the temperature difference in an average sense, and it's much better than the algebraic difference that we saw before. Of course, one of the objectives of heat transfer in internal flow, just like in external flows, is to find the Nusselt number. For the laminar flow, it's quite interesting. If you look in the books, there's all the mathematical derivation, and we find that the Nusselt number is constant in simple cases. For example, constant heat flux, the Nusselt number defined as Hd divided by K is equal to 4.36. In the constant surface temperature case, the Nusselt number instead is 3.66. This is for circular tubes in constant properties and fully developed conditions, so there's no dependence on the Reynolds number and the Prandtl number. And these two results can be found analytically by integrating the momentum and energy equations in the laminar case. In the turbulent case, of course, the situation is more complicated. And now we have a Nusselt number that depends on the Reynolds number and the Prandtl number. So this is a Dittus-Bolter correlation for smooth circular tubes. and the n exponent for the Prandtl number is 0.4 for heating and 0.3 for cooling, and it's valid for Prandtl numbers larger than 0.7. But in the literature and in books, we find many other correlations. For example, Petukov, I hope I'm pronouncing it correctly, it's a more accurate than Ditus-Bolter. And we have other correlations for liquid metals, for very small Prandtl numbers, for non-circular ducts, and so on. Okay, thank you very much, and I hope to see you in the next lesson. Bye.